Thank you, everybody, for joining on a Thursday evening. We have a lovely session on AI-driven observability for you all. To introduce our speaker, Monika Gupta. Monika is a staff engineer at Intuit, specializing in AI-driven autonomous operations. Her professional background includes roles at reputable companies such as Honeywell, British Telecom, and TCS. She holds an MTech in Artificial Intelligence and Data Science from BITS Pilani and has earned a quarterly Star Performer Award at Intuit for her contributions toward autonomous operations. Beyond her passion for IT, she enjoys traveling and cooking. She firmly believes that dedication and an innovative approach are essential to advancing in one's professional journey. Thank you so much, Monika, for joining with us today. And over to you.
Thank you everyone for having me here. I'll just start share my screen. Yeah, so as today, hello everyone, we are going to talk about AI-driven business observability here. To start with, let me first explain what the problem statement we had in Intuit and how we tried to solve it. So here in this snippet, you can see, right, there is a human who is continuously monitoring their screen, and every X minutes, they are just checking, like, okay, if there is any issue or not an issue. And then after a certain time period, they are raising a signal and then asking for certain actions to be taken. So we had a complex business use case where we had an Uber kind of network where various of customers, millions of customers, were needed to be served within defined service level agreements, which is SLAs. These customers were needed to be served within their required choices and skills. And there were scenarios where even after optimizing the matchmaking a lot, we were not able to serve them within the SLA. The scenarios like where the people had taken more leaves than anticipated, or there were differences between the projections versus actuals. So these were some unprecedented situations which we couldn't handle by simply optimizing the matchmaking. So here comes our requirement to have a troubleshooting system which can, handle these kind of situations and take the decisions at runtime. But in the current state, there were no defined system which could take these decisions, and there were humans there which were, handling this situation. So when we were trying to solve this problem, we started thinking about observability and what it means and how we can apply the principle of application observability to solve the problem of business observability. So observability focuses on comprehending the internal state of a system by analyzing its output. Observability does not only focuses on detection, but also the prediction. And the role of observability is it goes deep into root of the problem, and then it tries to identify the solution, not only just suggesting the solution, but at a very mature state, it should be able to take the decision by its own. So observability goes hand in hand, starting from the detection to the prediction to the diagnostics and ultimately to the decision making. So once we understood the principles, we wanted to solve our problem of humans taking the actions in a systematic manner. But this problem was more complex than application observability, because in application observability, there are systems involved. When there are systems involved and we receive certain actions, we receive certain signals, the actions are simpler to take because there is no human sentiment involved. But in this case, when we had the humans involved, there were a risk of, not satisfying the customer sentiment or not following the legal guidelines. Also consider like if there's a situation and we cannot just simply call a person to come back on the DAG and handle the situation because they're on official leave. So our objective was still the same, that we wanted to serve our customer within the defined time frame, take preemptive action before the issue occurs, identifying the root cause of the issue, and taking cost effective measures to address the situation. But we had three challenges. The first challenge was handling the scale of the system. So our data was coming from multiple sources. There were real-time sources as well as some sources which were not in real-time nature, like but they were computing the data at a certain scale. So there were more than 130 plus metrics which were impacting this overall demand and supply. The second challenge which we had was the complex network, because I'm talking about the millions of customers and the complex matchmaking tools which consider their choices and like which kind of uh, skills they want. So it are whatever we are trying to reduce the MTDD, it should honor that. It should honor the customer sentiment. The third challenge which we have was to remove this manual decision making layer and reducing the mean time to resolve. To reduce the mean time to resolve, we wanted to have reduce the mean time to understand as well. So it's like, once we have detected it, we wanted it to be resolved such that we can also explain it, like how and why the system has taken this decision. So here comes the solution architecture. So when we were thinking about the problem was not just that we wanted to solve it, but it was the root of the problem was there was not enough data. So first stage, what we started is we divided this whole problem into four pillars. The first pillar was data. The second pillar was detection or prediction. Third pillar was decision, and the fourth pillar was action. So to solve for the data, since data was coming from multiple sources, they were real-time sources and there were certain sources which were having this data present in a non-real-time fashion, and there were certain systems which were pushing the data to the data lake. So for the system which were already emitting the signal at a certain rate, they were pushing their data to a Kafka topic. For the system which were having the data at the lake layer, we built a batch processor based out of Spark, and we generated those events so that we can seamlessly ingest this data in a defined manner in our storage layer. Before ingesting the data, we want to have a mediator pattern here so that we have a common way of ingestion, and we can remove the unnecessary and transformation which we might need to take care in future upcoming layers like detection or prediction. So we introduced a Flink based stage processing layer which had three layers. First is transformer. The second layer was first layer was transforming the data. Second layer was adding or removing certain not required parameters. And the third layer was processing. We also build this layer in such a manner so that in future, if required, we can inject and use this layer to emit the data to any other storage. And our systems are not tightly coupled. Now, coming to the storage layer, we analyze the nature of our database. We analyze the nature of our data. We found out that our data is coming at a certain rate, which is associated with time. So we thought of having a time series based storage, which can handle this much scale of the data and can provide us real-time detection capabilities and also can serve our observability layer. So we thought we use the influx. We use the influx, I'm going to talk about that in our following slide. But in this architecture, we push these signals into our time series storage. Then from the time series, once we have solved the problem of the data, we we were thinking how to solve for the detection, because still they were humans who were taking who were taking reading these signals and manually taking the decision. So we evaluated many rule engines, and we wanted a rule engine which is configurable in the nature and can handle this much scale. So we made use of Grafana based rule engine here. But again, this was not a tightly coupled with our system. We build our system in such a way so that we can change the rule engine later point. And ultimately, that was also not our goal, because our goal was to build a AI driven system, not a rule based detection engine. But to build any AI based system, the first stage is to collect the data. So this detection layer was pushing the signal to our service layer, which has its own storage layer. And there we were collecting the data. Once we have enough data collected, we started building our prediction layer. This prediction layer was not focusing on the real-time signals, but it was getting the all of the signals which detection layer has emitted, and then we trained our models on this prediction layer. So initially at the decision layer, we just had a service which were taking the actions as well. And then slowly, since the system, understanding the complexity of the system, we divided this into detection engine, and then having multiple agents which can take these decisions, like lever recommendation, cost analysis, pulling the lever, or detailed analysis. So all of these layers I'm going to talk about in the following slides as well. Okay. So first challenge which we had was the scalability of the system, which I have just now talked about. So data collection, we had multiple sources there. So there were multiple stages which we considered how we can handle this much scale. So first step towards this was evaluating correct database for the storage. The second, which I'm going to talk about in detail in the following slide. The second pillar was efficient data management. So we wanted to build our data in such a manner so that we can our observability layer can handle it, we can handle the scale, and the way we store it, that is also optimized. We in the previous slide I have shown like how we had used Flink-based stream processing. So we follow the asynchronous event-based processing patterns to handle this much scale of the data, which help us not to choke our system when the data size is getting increased, or suddenly there is more load from real-time system is coming. The Flink-based system also helped us to reprocess the events whenever any failure occur, which I'm going to talk about in detail. And then we had this config driven onboarding for the new data sources, which is like when we had, which is like when we were onboarding many more real time sources, how we can quickly inject in the system without making much changes to any of the subsequent layers. For the flexible UI layer, we were thinking like, since we wanted, our focus was not to build the observability, but when we are building the Tesla, still we need, some kind of dashboard for the emergency situations where humans still have to take the actions. So we didn't even ignore the monitoring. We built the UI flexible layer, but we didn't invest in this much. So we focus on building this flexible UI layer from the available, you know, the market players, and we chose the Grafana for that purpose, which I'm going to talk about. Then we also introduce certain fault tolerance and resiliency patterns in our system. So we had this asynchronous event processing, but let's suppose an event got failed, we missed certain data points, or there are some certain discrepancies because we were reading the data. There are certain data quality issues. So for all those cases, we build certain fault tolerance and resiliency patterns, which help us to improve the quality of our data and also the quality of the overall solution. We focused on auto scaling. This was a microservice based architecture, and we follow the Flink based pipelines were able to auto scale by themselves. So we had also implemented the auto scaling in this case. Now coming to how we have come up to the InfluxDB, this is what I wanted to elaborate a little bit more. So we considered three databases, which were first was Postgres, like which is frequently used as a transactional store, but in some cases they can still serve for the analytics use case also. But we found out that if we make use of the Postgres, uh, we have to make some schema changes because that's a row-oriented storage. So whenever we are introducing a new column or a new metric or we are onboarding a new data source, we have to make the changes in a schema. And then if we are running any runtime aggregations, they are costly operations and and if the size of the data is used, like in this case, the data was in the billions or trillions. So then it requires a partitioning to be performed. And then partitioning can still go out of the hand when we had the new data sources to be ingested. And then there was a pre-aggregation required because if the data size grows, we cannot just have the runtime aggregations to be performed. So again, we had to ingest, if we have to go with Postgres, we have to have another layer which can do this pre-aggregation. There was another offering which is StarOps, which is an analytical DB, OLAP, and this is also SQL based. This also supports relationship between the tables and the runtime aggregation, since it's OLAP, it does not require pre-aggregation. It does not require data partitioning because with SQL, it automatically partitions the data when we define the indexes. But the problem was, since it was a SQL based, again it was using row based storage. So if if you're introducing a new data source, we have to make the schema changes. Then we also analyze Amazon Time Stream DB and InfluxDB. So we that was a OLAP. It was making use of NoSQL and it was also time series based database. And the important advantage of having the Influx was it was a schema-less DB. So in Influx, we need not to create our schema upfront. We can just create the buckets, which are the standard convention followed in the Influx. And then we can just name the measurements which we want to have, and then it can easily handle it. So with our transformation layer itself, we were able to handle like if any new data source come, we can just have a new measurement defined and ingest into the Influx. Again, since it was a OLAP DB, there was no requirement of having pre-aggregations, and we were easily able to query the data at the runtime, and it was able to serve our use case. So, and one more point was here why we consider InfluxDB the nature of the data, because there were many sources which were emitting the signals at the real time. So time was an important factor which was getting ingested with each data point. So we consider that and then we modeled our data accordingly and then we made use of the InfluxDB. Okay, so for the config-driven onboarding of the new data sources, we made use of we made use of the Flink. So Flink is a powerful stream processing engine. It can handle, uh, stage-wise event processing, and it comes with, dynamic scaling features. So that's why we chose the Flink for this real-time signals processing, and it also comes with the feature like if we have to reprocess the event. So we had a Kafka topic where we could easily reprocess those events. Then we had this a transformation layer which was based out of Juke. So this transformation layer helped us to transform the data which was coming from multiple sources in different format in the from the different signals in a unified format. Because when we had to ingest the data into the DB, we wanted a uniformity. And this layer also helped us, like if we have to just had a new data source to be plugged in, we can just create a new transformation layer and all of the layers could can easily handle the new data source. So we created those transformations and Juke handled that very seamlessly. The third we did was upsampling of the data. So initially, when I was showing the architecture, there were two types of sources. One was real-time source, and then another one was the batched or the non-real-time sources. Each of the system were emitting the signals at a different grain. So real-time sources were emitting the data at 1 minute grain, and the batch sources were emitting the data at the grain of half an hour or 1 day. So when we had to compare this grain of the data, we cannot compare because their time scale is different. So to fill the gap between these two grains, we upsampled our data such that we can compare these two different grain data sources. So we followed these steps. We first transform the data. Second, we had the second stage of the Flink, which decorate the data. Third, which was upsampling or downsampling the data. And fourth, through which we can ingest the data. We made this ingestion also in such a flexible manner so that in future, if required, we can make use of this system to emit the data to another layer. Okay, so after making all of the changes, how we have handled the scalability, how we have handled the auto scalings, those fault tolerant and resiliency patterns, and making use of asynchronous event processing, how we have created our InfluxDB for a time series based storage, the scalability numbers were, were looking good. We were able to handle the TPS more than 500. We were able to handle the matrix, which are more than 130 plus, and we were able to handle 200 million events without any failure. So we were able to write the data. We also implemented some of the observability patterns here and alerting and monitoring such that if any issue occurs, it can raise a signal. Okay. So the second pillar in the solution architecture was detection. So when humans were detecting, they were continuously monitoring the screens and they were trying to identify the issue, and we wanted to first go away with that. So we took a stage-wise approach where we first developed, where we first used already available issue detection layer. So this issue detection layer, we made use of the Grafana, which the snippet shows here in the right-hand side. And we were able to create the query and alert condition at the runtime. So Grafana not only helped us for the visualization, but it also helped us for the alerting as an engine and the custom logic to have any kind of detection. But that was not our goal. We needed that kind of a data or detection layer to start with, but we wanted to go away with that and predict the issues because always uh, you know taking the preemptive measures is better than taking the reactive measures. In the preemptive measures, we have enough time to react. If we have a system which could tell me based on this incoming signal that, okay, now your system is going to breach SLA, or you can take these measures, I can even reduce my MTDD. So by introducing that detection layer, we almost reduce the MTDD to zero. because now no longer human layer were detecting the issues, but we even wanted to be detect or predict the issues 30 minutes or more than that before. So we assess the rule-based issue detection system. We first define our objective, and then we evaluated the data, and then the next step was choosing the appropriate model. Then the next step was training the AI model on the process data, and then checking whether the AI model is performing as expected or not. And then we deploy the model. This is a generic way of looking into any AI model. We applied those principles when we were also doing this issue prediction activity. Okay, so when we did the issue prediction, we have already data present in our time series space storage, and we have already pre-processed the data. But during time of prediction, we even analyzed that pre-processing also was not sufficient to train the model. Since the data was real time in the nature, it was impacted by the seasonality. It was impacted by the time, like if it is the start of the day or the end of the day or middle of the day. So it was impacted by seasonality, or it was also impacted by certain period, certain months in the year which has the more traffic, then certain months in the month which has the lower traffic. So our first task was to clean up the data, and then also identify, since we have 130 plus metrics, so we wanted to build a correlation, like which metrics we can. There were multiple kind of issues which we were detecting, like some issues which were based on how, how we reaching the SLA more than 90, 80. So different kind of issues we were predicting. So for each type of issues, we wanted to have the correlation, because there are 130 plus metrics. So out of them, how many was related for the issue? So we first did the correlation analysis between the metrics. The interesting thing which came out of this correlation analysis was the metrics were not dependent at the same time, because these were real-time signals. So what has happened half an hour before or 1 hour before or 2 hour before had impacted our data or had caused this issue to happen. Since this was the important factor when we were doing the feature engineering, we identified we used a principle of temporal proximity to generate certain features. So temporal proximity is a principle which tries to identify, like, how far is my system is from its base condition. We applied that principle to identify, okay, if how far was my condition 2 hours before or 3 hours before, and we applied the same principle to define a new metric or new feature for our model, which was a rolling severity. That feature was not only considering the current interval, but it was also able to consider our previous interval, like what was happening 30 minutes before, or last minute before. Like, it was able to handle those cases. We also did some outlier detection, like I was talking about seasonality, or which time of the day, morning, evening. So because there were so many, spikes in the data, so we removed those spikes. We applied those data engineering, machine learning principles to handle those cases, and then we did the feature engineering. Finally, when we had the enough features, we evaluated the two models. First model was profit, because profit, considering the nature of the data, since profit is statistical model, and it can handle the seasonality, like profit can automatically detect and account for seasonality in the data. It can consider for the holiday effect, and it can handle the miss data or the outliers easily. So we consider the profits. Another model was LSTM. So LSTM is a recurrent neural network which is essentially suited to a sequence prediction problem. LSTMs are designed to avoid the long-term dependency problem. But when we compared the result, we found that LSTM was performing better than the profit because considering the number of metrics we have, it was a very complex use case where profit could have been better when we had the lesser number of uh, features to be considered while training the model. So we use the LSTM for our initial version, and we are still exploring a better model, which or we are trying to have this LSTM model with more, neurals, so that we can handle it, we can predict it more better. The below architecture shows simplified version of our model deployment state, like how we did the model deployment. So we had the influx database. We pushed this data out of influx to the S3 bucket, and we deployed our trained model in the SageMaker, which is Amazon SageMaker. And then from the Amazon SageMaker, it was continuously running every 15 minutes to predict if issue is going to happen in real time. And then we were emitting those signals to the Kafka, and then they were read by our service, which I have shown in the previous slide. So with all of these changes, our MTDD was looking very good. We had improved our accuracy of the monitoring to 100% because now we had a detection layer as well as the prediction layer. And with config-driven data source onboarding, the Grafana-based issue detection layer, we were able to solve up to 6,000 human hours of the manual effort. Whatever the training and feature engineering exercises which we did, through which we were able to achieve the precision of 89%, recall of 91%, and accuracy of the 82%. Since this was a issue detection model, we wanted to optimize the precision and recall then accuracy because we wanted to decrease the number of false positive. This false positive would have created more noise on the floor if there were issues which were detected and they were false, and if humans have or systems would have taken the action. So our main goal was to work on the recall and the precision. Okay, so we had reached to the last pillar, which is taking the action. So we didn't really first at the very first place build any agents. We first built these guided workflows. So these guided workflows were created based on the inputs which we had received from the humans and what they would have taken decision based on certain situations. But these were very static in nature. Like these were based on the experience they were created, and they were not able to amend their decisions if any, you know, uh, they were not smart enough to amend their decision based on the past issues. They were not having any feedback loops in place, and they were not even considering the cost of taking the actions. So these were very static in the nature, but we started with that. We collected the data of these guided workflows, and that helped us to build our AI agent based layer, which could, take the actions by its own. Okay. So this is the flow diagram of how we are planning to reduce the MTTR. So we had this Camunda based workflows, and we did the gap analysis to identify the areas for AI integration, and then we build this AI agents based workflows, and then we did the deployment, and based on the outcome we optimize it, and then it goes again and again. So currently still we are in optimizing phase, but we have developed a kind of architecture which is going to improvise in the future. And currently these AI based agents we are planning to run with humans so that we can compare the decision making of humans versus AI agents and improvise in upcoming future. So this is the uh, architecture of this guided workflow look like. So here in this case, there is a supervisor AI agent, and there are this uh, we had followed this hierarchical based agent architecture here, where this supervisor is calling this subordinates like diagnostic agents or action recommender agents based on, and then one by one calling the other agents. So we used vector database. We created the knowledge base for these diagnosis agent, which was based on our previous data and some of the input which we had taken from the humans based on their experience. And they were making use of LLM to ad, to query this InfluxDB at runtime to gather the data. So first agent was diagnosis agent. The agent was querying the InfluxDB, and it was uh, trying to identify why the issue has happened. And if after understanding why the scenario, like it is mainly about the mean time to reduction of the mean time to understand the issue. So once this diagnosis agent has understand the issue, it sends the whatever the understanding to supervisor AI agent. Next comes the action recommender agent. This agent is going to recommend like, okay, this is the situation and what are different type of actions I have according to this situation and this diagnosis. For this issue, this action is best suited. Considering the common workflows, like these workflows were like predefined workflow, they would have taken the step-by-step measure. But this agent is smart enough, so it can make use of this knowledge base, which is getting updated frequently also. This to understand last time this when this issue happened, this action was taken, and the previous this agent is also sending some cost-based signal to this vector database. So it is considering all those signals, which is it is also considering the cost. It is also considering what is the best suited action for this situation and then recommending a correct action. Third agent is an action executor agent. So once this recommended agent is, has recommended the correct action to be taken, this action executor agent is taking the appropriate action. It's invoking one of these services at without, and it is able to make these calls at runtime through invoking the REST APIs which we had. And finally, when we had this, all of these agents completed their task, then there was a agent which is calculating the cost of this whole process. So once this action recommender agent has redacted the action and this executor has executed this action, how much time this action has taken to complete, and how many changes did I make to overcome the situation? How much time it has taken from that issue to resolve? So it is taking all of those actions and it is calculating a cost or certain signals, and then it is standing to a service, and then finally a lambda function runs, and this also updates the knowledge base. So ultimately this is a feedback loop which goes to this recommender agent again, such that next time when it is going to recommend the action, it can also consider these signals which are coming from this action executor agent. And we made use of LLMs to which help these agents to generate this query the system at runtime. When we did this whole exercise of migrating from a human driven process or a manual process to an automated process. And when we did this AI based migration, there were certain learnings which we have got. First is the quality of the data is very crucial. When we did this pre-processing, cleaning, normalization, augmentation, this significantly impacted our model performance. The second point was choosing the right model architecture. And this is an iterative process. There is no clear cut guideline which says that, okay, in this model can behave better. But it depends on the complexity. It also depends the nature of the data, and it also depends interpretability and the performance. And then selecting appropriate evaluation metrics is also important. In our case, we were focusing on precision and recall, but in some cases, it's needed to focus on some other evaluation metric, which could be accuracy or F1 score. So it is important that which evaluation metric is being used to ensure or assess the AI agent's capabilities. And then the last thing which cannot be compromised is ethical concerns, such as privacy, security, and fairness. So when these AI agents are suggesting certain actions, it should not be biased towards certain people or certain regions. We wanted to make sure that we are following the ethical guidelines, and we also don't want to take certain biased decisions because this can foster the trust of our customers. Since we are coming to the end of our session, this is what one thing which is very inspiring to us was what is the difference between monitoring and the observability? So monitoring is like seeing the tip of the iceberg, where we just see what is happening on the top. But observability dives deep into the unseen layers. And with this, we were able to observe our whole of the network and serve our customer in a better, in a proper manner. Thank you, everyone. If you have any questions, then we can discuss about it.
Thank you, Monica. Thank you so much. I've opened the floor for any questions. Y'all can either put it in the Q&A or in the chat. In the meantime, before Monica takes any questions, if everyone could put on their camera if you can, so we can take a quick, just a picture for the session, if that's possible. I'd also like to thank everyone for joining. I know tomorrow onwards is a long weekend, but thank you so much for joining. All right, I'll assume that the rest can't start their camera. That's no issue. I'm just gonna go 1, 2, 3, and cheese. Ready? 1, 2, 3, smile. All right. And yeah, now we can take any questions that you have. I also think it was a very, very interesting and sort of to the point. So maybe we might not have too many questions. I think people are still grasping the information. I'll keep the floor open for 2 more minutes and then we can wrap up if there aren't any questions. Also, for the folks asking me whether we will get the recording will be up on our YouTube channel. I'll put the link to our WhatsApp here, where as soon as we upload, I will send a message there. So 1 second. Here.
Yeah, Monica, I have a question.
Please.
Yeah. So actually, I had a doubt. Like you have explained, to have the monitoring and the observability. So can we use this observability using AI to the infrastructures. Like we have infrastructure at our organizations, like servers and hosts and so on.
Yeah. So interesting question. And yes, so this observability is not only a principle which is applied to a business observability, but it is also applied to application or system level system. In those cases, your choices might be different. Like you might want to choose a different data storage, or you might want to choose a different model when you are doing this. There are certain, layers in the market which are already solving this obscurity problem, and they each of them has solved in an interesting manner. So yes, these but the principles remain same. So whatever we have discussed about the observability principles, those remain same in any of these cases.
Okay, so like as you have mentioned, like we will be getting alerts before the issue occurs, right? So in case of infrastructures, like how can we get this?
So consider, let's suppose you have a container or a pod running,
Mm-hmm.
and you have deployed your container or pod in a Kubernetes, right?
Mm-hmm.
So if your container is emitting, uh, there are certain metrics like how much is the CPU utilization, how much is the memory utilization, and if those signals container is continuously emitting, and you have uh, built a layer which emits those signal, and you store those signals into either Prometheus or Influx or any other data layer, and then on that layer you can build those rules. So let's suppose you say that, okay, when my CPU utilization goes above like more than 50% or more than
Mm-hmm.
60%, and then you want to take certain actions. So actions could be like, you want to scale up your pods. Automatically it should happen, but there are scenarios where your whatever the scaling you have done, it's not sufficient. You want to throttle your traffic, or you want to close certain channels. So these are the manual actions which can be taken. You can even automate this, like you can have your observability dashboards built on it, which you can connect to the pager duties, right? So those pager duties can uh, ask your developers or your system users to come back on the floor and make handle the situation. So many organizations, like including Intuit, has followed these patterns.
Okay. Okay, thank you.
All right, I see one more question, Monica. It's how did you take care of customer data privacy? That is a major concern in training ML models. Can you share more on that?
Interesting thing is, in this case, we were mostly dealing with metrics. We were not dealing with directly with the customer data. Like it was mainly related, like how much time customer was there in call, or how much time uh, from which region the customer belonged to. But it was not holding any PIA or sensitive information. So interestingly, in this case, we need not to worry about this, information. But there are certain cases where these situations occur. So in those cases, as a practice, we mask the data. We don't directly make use of the customer data, but we build a masking layer which could mask the customer data. And if we want it, we can use those uh, data to train our models. But still, there are certain cases which require your customer to agree. Like if you can train your data on their like sensitive information. So many websites, if you see, they ask you for if you agree or don't agree to train your data on their uh, whatever the customer sensitive data is coming in. So these are some practices which are followed across industry.
All right, I think that answers that. Um,
Hi,
Monica,
Arushi, I want to ask another question. So,
yeah.
Monica, can you please tell me, like when we have huge amount of data, so how can we do this masking practice? Like, how feasible would that be considering the scale of the data?
Yeah, so if you see, there are certain ETL tools which are available, and if you are going ahead with S3, you can like there are certain Informatica, certain tools which are already having these capabilities of masking it. But if there are no ETL tools, there are certain already tools available which can help you do this masking activity. You need not to do that manually or by writing the scripts. So we can just explore certain tools which are available and which can help you to do that.
Okay. Also, I wanted to know, for training purposes, do you use just the real-time data, or do you also use some synthetic data for the purpose of training?
So for our use case, we had both. Like we had real-time data as well as the data which was already batch data, right? So obviously for training, the real-time data is just not sufficient because we needed huge amount of data, and when to model to behave properly to understand all the scenarios, it's always good practice to have a good amount of data to train the model. So as part of the first exercise, we first collected the data, stored it, and then took the this training exercise to train our models.
Okay. And just lastly, when we have multiple matrices, right, as you mentioned, you had 130 plus matrices. So how to deal with them simultaneously? Like we can have various combinations. So how do we consider those multiple combinations when we create the various rules at Grafana level?
Yeah, so at Grafana level, yeah, we also face a similar issue, right? When we had to create this detection layer. Exceptionally for the influx, it was not supporting. But with certain databases like Postgres and all, they their detection layer can handle this cross joins. So this Grafana is just a rule engine, right? For our use case, we need not to join it to multiple, measures. But if you had such kind of use cases, either what you can do at influx layer, you can create those pre-aggregated tasks which can put it into single measurement, and on top of it, you can create your rules. If that is not something which you can do, you can have subsequent rules defined. Like you create first rule, and then on top of that, you wanted to have certain rules. So these kind of things which you can do with Grafana. There are certain other rule engines also, like if let's suppose Grafana supports this Prometheus and Loki based, uh, which has the more advanced features which Grafana does not support. So those also you can explore.
All right. Thank you so much for that, Monica. Is it okay if I can share your LinkedIn profile for anyone who has additional questions?
Yeah, please you can share.
It's on.
I have a question. Can I put that to Monica, or do you have time to answer to that?
Actually are short on time.
Okay.
About
Maybe
this,
I'll contact her in LinkedIn and meeting.
yeah, you can put it on LinkedIn or you can put it on our WhatsApp group, and
Yeah, sure.
on both, she can take it there. Does that work?
Yeah, sure.
All right. Thank you so much for joining. Thank you so much, Monica. Like you can see, this was quite engaging. You had quite a few questions there.
Thank you,
Thank you,
everyone.
Monica, for doing this for us.
Yes,
And
thank you so much, Monica and Arushi as
Thank you,
well.
everyone. Have a great day and happy weekend.
happy weekend. Thank
Happy
you.
weekend, everybody. Happy weekend.
Yes.